I-91 Springfield Viaduct Structural Life Extension. Our presenter is Tom Weinmann. Tom is Vice President and Practice Area Leader in Structural Monitoring for Geocomp and leads their Chicago office.
It's a diagnostic test, but it's a real-time test. It's not a scheduled load test, but it's through live strain measurements of live loading of a bridge structure. Presentation outline, this is the I-91 Springfield Viaduct. We'll talk about where it is, what it is, the problem, CME investigation. CME Associates was the engineering firm that led this investigation. Instrumentation plan, structural health monitoring system, talk about the dynamic response and the data analysis captured, results, conclusions, and then hopefully some question and answer period. The I-91 Springfield Viaduct is a viaduct. It was built in the 60s. It's located in Springfield, Massachusetts, the far west side of Massachusetts, Springfield, home of the NBA Hall of Fame. 3 lanes per section, traffic volumes. It's a critical part of the interstate highway system serving this area. As you see, it's not a very pretty structure. It's a pretty long structure, approximately 4,400 feet in length, elevated viaduct structure. Problem was Mass DOT had an annual maintenance budget cost of about $2 million, and it was increasing on this structure. Primarily, the whole road deck system had to be replaced. That was the #1 priority of the structure. They also evaluated the structure. The superstructure is primarily composed of a number of non-redundant members as classified by AASHTO Bridge Design Code, and as non-redundant members they have a lower fatigue stress range than redundant members. And as we know, stress ranges as calculated or determined by modeling often have some conservatism in them and can be much higher than or more conservative than actual field measured stress ranges. So that's really the primary purpose of this talk. The full replacement or relocation would take too long. As you see, if they had to go and replace the whole superstructure, it would be extremely cumbersome, not only in dollars, but inconvenience, traffic closures, rerouting, etc. 2 parking structures exist within the bridge limits. The estimated full superstructure replacement was $800 million. CME was responsible for the investigation. They had done the bridge inspections, had done quite a bit of analysis of the superstructure, and they led the effort to investigate the possibility of structural life extension of the superstructure. The substructure condition, foundation, everything was fine. They had no issues at all. The viable full deck replacement with precast panels from a structural capacity standpoint. So that's how they were going to replace the road deck, using accelerated bridge construction. I don't know if any people are familiar with Mike Como with CME. He's one of the innovators in ABC. Does a lot of work in accelerated bridge construction. The investigation also included to calculate the stresses and compare with infinite fatigue life thresholds listed in the AASHTO bridge design specifications. Can we save the superstructure? Can we mitigate repairs at least for the superstructure? The investigation consisted of evaluating 85 spans containing girders with partial length cover plates, an infinite fatigue life threshold limit, 2.6 KSI, calculated fatigue stress based on calculations and modeling was 3.4, not good. It exceeded. There's some problems, potential problems. Virtually every span contains fracture critical cap girder sections. And the bending stresses in the bottom flange of cap girders had some pretty high fatigue life threshold limits. How do you retrofit? Do you verify these values to lead you down the path of the proper retrofit options? Some of these options included bolt splice places. Well, you can see here for the different types of concerns, they had evaluated rehabilitation options. So some of these can be strengthened, some of these can be retrofitted. Those are certainly all viable options. Or you can use structural health monitoring, utilizing strain gauges for counting stress cycles. Evaluate the true fatigue limits or the measured stress ranges that this structure is seeing. So a fatigue life investigation was undertaken, conforming to ASTM standard 1049, breaks counting method into logical loop steps, developed an algorithm to process large volumes of data, fully automated processing for daily analysis of the incoming data, continuous monitoring of over 200 strain gauges at 200 hertz for about 14 days. Shows some of the locations, some of the instrumentation locations. You're seeing the cross-section where they tried to locate representative cross-sections across the bridge structure, and in all cases, they captured the worst scenario of the heavy truck lanes over to the side. So it was representative for all live load traffic, including any heavy truck loads. Installation of strain gauges on the hanger plates. 48 total. They were concerned about the hanger plates appeared to be frozen. You'll see some results from some of that testing. So these hanger plates were not allowing rotation of the bridge hanger plates as designed. Installation of strain gauges on the floor beams. Spot weldable strain gauges. In all cases, as a steel structure, we use spot weldable strain gauges. In all cases, use 36 total on the 3 floor beams. You can see some of the installation, the cross sections across all the stringer beams, close to the ends where the splice plates were, typical application. Structural health monitoring system took the sensors, ran them through a high-speed data logger system throughout the structure. The high-speed data logger system connected to a field PC that processed the data on site and then transmitted the data to our server in Acton, Massachusetts. Here's some representative data. Here's some hanger plate, girders 6 through 616. These are, although they're not, they appear that they're not on zero. We adjusted the data plots so they're not all superimposed on each other, but just assume each color is represented starting on a 0 at the y-axis. So you're seeing some of the stress, the KSI, the computed stress in those members from live traffic loadings. Blow up of this, so what you're seeing here are the bending strains of the hanger plates, a little blow up of that little section there over a very short time period. Seeing the reversal of the bending strains. So these are processed through a rainflow analysis, doing a stress range count of the different stress cycles for this type of strain gauge. And then same thing with the floor beams, calculating the stress ranges for the floor beams under ambient traffic loading, a blow up of that section as well. You're seeing the strain gauges on the top of the cap girders or the floor beams and on the underside of the floor beams. Again, they're processed into a rainflow analysis to determine the number of cycles. And then the same thing with the girder with the partial length cover plate. You're seeing the peak strains that are captured under live load, all representative data plots to see what we actually do with the data. So the rainflow analysis, it uses Miner's rule, similar to what we saw in one of the earlier presentations, to determine what the constant effective stress range was for each of the worst case scenarios. So really the results, CME was primarily focused in the worst case results or for the highest stress ranges that were calculated. So here's an example of taking that information, mid-range stress range, percentage of the total, and how we come up with a constant effective stress range. So the conclusions, all the locations gauged resulted in a constant effective stress range that was less than what was specified or required for the infinite fatigue life thresholds listed in the AASHTO LRFD bridge design specification. So you can see for the hanger plates, the maximum measured was 1.78, much less than the infinite constant effective stress range required, 0.821, much less. So again, you're seeing, similar to what Travis was pointing out, you're seeing a lot of interaction of the various members that really you can't determine through calculations or modeling, but is best measured using actual field data. These are the thermal effects on the pins and hangers gauged over a 7-day period. You can see these are just thermally induced cycles without the live load data. The live load data really was minor compared to the large temperature swings that we were seeing from the hanger plates, the restriction of the movement in the hanger plates. So it really proved out that the pins and the hanger plates were frozen and really need to be modified. All the locations gauged were less Determined the service life of the steel structure could be extended at least 30 years. Eliminating the need to replace the entire bridge, made the proposed deck replacement project viable. Removed the conservatism inherent to the fatigue life formulation. Confirmed the concerns of frozen pin hanger assemblies, allowed them to proceed with some design alterations or retrofit options for that. Eliminated potential load posting or repairs, and probably most important is reduce the cost of the rehabilitation from an estimated $800 million to $260 million by implementing a $180,000 structural health monitoring program. Acknowledgements is Mass DOT, Mike Como, principal with CME Associates, and Timothy Young was the project engineer we worked with on this project with CME. Thank you.
The preceding was produced by the National Center for Pavement Preservation. More information can be found on the web at pavementpreservation.org. Additional support provided by Michigan State University.